Hello everyone, my name is Dylan Britton and I am interning underneath Frank this spring semester. Today I just wanted to give you a quick overview of how our multispectral imaging pipeline works. So first, we should have a brief understanding of how multispectral imaging works in the first place. Instead of seeing red, green, and blue channels like a typical RGB camera, multispectral cameras are designed to capture image data within other specified wavelengths along the electromagnetic spectrum. As such, these camera sensors can be designed to capture image data outside of the range of visible light. By utilizing this technology in combination with AI/ML efforts, we hope to develop a solution to replace pre-existing wearable biosensors. By training deep learning algorithms to recognize differences in multispectral data, it may be possible to determine parameters like cognitive load, emotion, and level of stress solely from image analysis. I would like to quickly detail the data processing pipeline that we have established thus far. The first step in our pipeline is to capture initial data. I have been working with an 8-band near-infrared multispectral camera that Frank had acquired prior to me starting my internship. Initial testing of this camera was conducted with the manufacturer-provided software called Second Look. We can use Second Look to easily demosaic this multispectral image and individually view the 720 nanometer, 760 nanometer, 795 nanometer, 830 nanometer, 870 nanometer, 905 nanometer, 940 nanometer, and 980 nanometer wavelengths. This software provides an easy way to collect data, but it's limited in the ways you can process it. We started by pulling recorded data from Second Look into MATLAB and processing it there. First with single images, then slices of videos. Eventually, we fully moved to collecting data within MATLAB to consolidate everything and streamline the pipeline as a whole. We start by collecting, tagging, and color mapping data for which to compare other data with down the line. I should also mention that to utilize this camera, the subject must be lit with a light source that matches the camera's perceived wavelengths. For early developmental testing, we have simply been using an industrial halogen lamp. For reference, halogen lamps put out light at about 950 nanometers. After collecting, tagging, and mapping initial data, we run the data through a visual bag of words algorithm that Frank had created in the past to act as our AI in predicting future data. Lastly, we use our AI to predict what new multispectral data is based on the tags established prior. Currently, we are able to distinguish between shapes, people, and color, though we still have our fair share of issues. Since initially starting development on this project back in February, we've been using a simple industrial halogen lamp to light our subject. This works, but it's clearly not ideal. This lamp heats up very quickly and is very bright, causing the subject to be uncomfortable during the duration of the testing. We are currently looking at near-infrared LED arrays to replace the halogen lamps to hopefully remedy this issue. Additionally, further testing and development time must be dedicated to further improving our image detection model. In the future, we aim to be able to use this pipeline to detect changes that are invisible to the naked eye, things that only multispectral cameras can see. But the technology is here, and it is possible. In short, it's an exciting time to be a developer at NASA. Though my internship is ending here in a few short weeks, I look forward to seeing what Frank, his team, and future interns can do with this project.